All right, what's going on, guys? Again, if you like this kind of content on learning more mathematical details of and more advanced topics in science, quantum field theory in particular, visit my Patreon page or hit that subscribe button. Let's get right into this. So we're talking about the projection operator today. This is an extremely important operator. It's going to help us go between bases of states, right? So suppose we have a basis. Suppose we have a basis and it looks like this. This is our G basis, right? So I'll say G basis. Again, the basis can be thought of as the orthogonal vectors within some orthogonal plane, or not plane, but within some Cartesian system, right? So you have your E1, E2, E3 basis vectors, but those are arbitrary, right? We could have, say, a G basis where we have a G1, G2, and G3. Right? And suppose G1 is 1, kind of making these up, 1, 1, 0. Well, this is actually the example I think that's given in the book. Suppose G2 is 0, 1, 0. And G3 is 1, 0, 0. Again, these are just an arbitrary choice of vectors. You can do this with any vector. Suppose we had another basis, right? Or we had a vector living in some basis that had our E1, E2, and E3, right? And this is our typical 1, 0, 0, 0, 1, 0, and 0, 0, 1. Right, and we have a vector living in this basis, which is going to be, let's say, 1E1 plus 3E2 plus 5E3. This can also be written as 1, 3, 5 in this form. Okay? This is all we're going to deal with, right? Two bases and a vector. We want to know what that vector looks like in the other basis. That's the point here. What we do is we can really just do G1 dotted with V, right? So we want V, take the dot product of that V with the other basis. The way we do that, again, is by doing 1 half 1, 1, 0 times 1, 3, 5, right? Where this is G1, right? So G1 dotted with V here's our V, here's our G1. Right? I'll write that out more explicitly. There's V. These are vectors. Okay? And that's a vector. Well, this is going to equal 4 over root 12. Or 2, not 12. 4 over root 2. You can do this multiplication. It's not terribly difficult. Okay? We can do the same thing for G2. G2 dotted with V. Well, that is going to be 1 root 2, 1, negative 1, 0, 1, 3, and 5. And that is going to be negative 2 over root 2, like so. And so V in the G basis, right? So we're taking each basis vector in G and performing an inner product on V to get what V would look like in the G basis. Okay? What V would look like in the G basis, we'll say in G like this. Well, that's going to be 4 -2, root 2, and then you can do it for the other basis vector, right? So that's what it's going to look like in that basis. So how can we make sense of this now? Well, we have what we did, again, was we did Gi dotted with V. These two things were vectors. Okay. What these gave us were the coefficients on the basis. So the basis again was Gi, right? So again, this here gave us these coefficients. And if we want to write the vector out in its entirety, we need to put the basis vector hacked on there as well, because again, when we write these kind of things, we said VI was equal to 1E1, right? Plus 3E2 plus 5E3, right? So we need these right here, and that's this right here. These coefficients again in the G basis were calculated right here. So these are the coefficients. This is the basis, the new basis. New basis on the coefficients, right? So what does this mean? This means V in the new basis equals a sum on I going to have it go to infinity. That's not how that's written. We start at I and we go to N, right? N could be infinity, or it could be some finite dimensional Hilbert space where these things, again, they're coefficients, mathematically speaking. Physically speaking, in physics, these are probability amplitudes, right? So probability amplitudes to be in some Hilbert space, or to be in some Hilbert space that describes some sort of state. Again, this is, I'll be a little bit more complete actually in the old basis. Okay. This is really what this is the projection operator. The projection operator is actually right here. Okay. So this here is the projection operator. The projection operator, again, is something that projects a vector in one basis. It's being described by one basis to the same vector. It's the same vector, it's just projecting it to a different basis. And you can do this for different basis states. Right? In quantum mechanics, we're just rewriting a few things. It's typically seen as something that looks like this. Right, where this is that inner product, this is the new basis, right? And typically this is seen as that as well. But again, so the operator here is this thing. That's the operator. It's the projection operator. operator, and it's very important in quantum mechanics. And I'll leave it at that. This video is going to be a little bit shorter than usual because I'm trying to break things up a little bit nicely. And the projection operator is sort of that one thing in quantum mechanics that could have been taught in the previous video on all of the operators, but then that might have been a little bit long, and I don't know. Whereas it doesn't really fit within the context of what we're going to talk about next, which is harmonic oscillators. It all sort of fits together, but if we want some organization to keep this in our heads a little bit better, I'm just talking about the projection operator in this video. So I'm going to call it here. Again, if you like this kind of stuff, you can hit that subscribe button. If you are if you want to contribute to this channel, you can go into my Patreon page. And so with that being said, I will see you guys in the next one.